Today we're going to talk about confidence intervals for a proportion. And so first thing, to get some definitions out of the way. So a point estimate is a value that I get from a sample. So let's say that I want to know the proportion of people that like chocolate ice cream. And so I might take a sample and find the percentage or proportion from that sample. That would be my point estimate for the population proportion, because I don't know what the actual population proportion is. And so I'd get that value using this formula here. So I'd ask maybe 1,000 people, that would be my N, and X would be the number that say that they like that chocolate ice cream. And there's my point estimate. And something we're going to need later, so I'm throwing it in right here, is, so P hat is our population proportion for successes, whatever we have defined as a success. And the number of failures would be people that don't like chocolate ice cream in this case. And so that proportion would be Q hat. Now, a confidence interval is an interval that I think that the population proportion is actually in. And with the confidence interval, there is a level of confidence that tells me just how certain I am that that population proportion is in there. Usually it's 90, 95, or 99%. So you can see here I have this interval. My sample proportion that I got from sampling goes right in the middle, and then I'm going to calculate an error that tells me how far to the right and to the left my confidence interval goes. So here's just an example. We're going to pull apart all the components of it. So a random sample of 1,008 adults from across the United States were asked the following survey question for a poll. All in all, do you think that things in the nation are generally headed in the right direction, or do you feel that things are off on the wrong track? And of those respondents, 222 of them said headed in the right direction. So based on the data, we did all the math and we got a confidence level or confidence interval at 95% confidence that we think that population proportion of US adults that think we're headed in the right direction is between 19.4% and 24.6%. So just identifying some things here, the point estimate for P, the population proportion, would be P hat, which is taking the 222 and dividing it by the total sample size, 1,008. So we get about 0.22 or 22%. The interval estimate for P is the two numbers at the end there, the 19.4% to the 24.6%. Those two numbers that enclose our interval are the lower and upper limits for the interval. And our confidence level was the 95% or 0.95. And so I'm going to call that C. So those are all the parts of a confidence level. But now we got to figure out, okay, well, what were the formulas we used to get that answer? So error, I mentioned that we had to get an error along with our population or sample proportion. So the error just tells us how accurate our interval actually is. It's telling us how wide it is. Sometimes it's called error bound or margin of error. All those things mean the same thing. Calculating error varies depending on the population parameter. So here we're doing a proportion, but I could be doing this for a mean, and then I have a completely different formula to calculate the error. So for proportions, this is going to be it. Error is going to be equal to some z-score that is based on the level of confidence, times the square root of P hat, that sample proportion, times the Q hat, the complement of P hat, divided by the sample size, all inside of that square root. Once I get that error, then I'm going to go back to that sample proportion that we got, P hat. I'm going to subtract the error from it to get the lower limit and add the error to it to get the upper limit. And then if I wanted to write it in interval notation, it's right here. Now this interval is always going to look like this if I were to draw it on a number line. P hat's always going to be right in the middle, and then my upper limit on the right and my lower limit on the left. So let's do a full example and calculate a confidence interval. To estimate the proportion of students at a large college who are female, a random sample of 120 students is selected. Okay, so we already have our first value. That's our sample size. We asked 120 people. There are 69 female students in the sample, so that's X. Construct a 90% confidence interval for the proportion of all students at the college who are female. So p hat is just going to be taking that x divided by the n, so we get about 5.75 for that. And the confidence level was 0.9 for this one. Okay, so thinking about that error formula, that's the first thing we need to do is come up with that error before we can get the upper and lower limits. So I'm looking at what I have and what's in there, and first thing I see is I don't have a z-score. So first thing we have to do here is find that z-score. So remember, the confidence level is it's a probability, and it is the area on our normal curve. Specifically, it's the area in the middle of the curve. So 0.90 is the middle portion of my confidence interval. And so the z-score that I need is right here. And the negative of that z-score also shows up on the left. And so I need to come up with an area that I can plug into my calculator to find one of those two z-scores, and then I'll just take the positive of it to plug into my error formula. Now, the function in my calculator usually only allows me to find a z-score given an area to the left of that value. So the easiest one to come up with would be this area to the left of the negative z-score. So if I can figure out what that area is, I can plug that into my calculator or into Excel and come up with that negative z-score. Then I'll just drop the negative off when I plug it into the error formula. Okay, so we got to do some thinking here with the area. The total area under a normal curve is 1. And I've got the middle 0.9. So if I were to take 1 minus the 0.9, I'd have the area to the left of the negative z-score and the right of the positive z-score, the two tails on the end. Now I only need one of them, but since they're symmetric, they have the same area on each side. So if I take that 1 minus 0.9 and then divide it in half, that'll give me just one of the tails. So that's exactly what we're going to do. The area that I need is going to be 1 minus the confidence level divided by 2. Now the great thing about using the standard normal distribution is that this is the same every time. Now, unlike a t-distribution, which changes with the degrees of freedom, standard normal is exactly the same every time. So once I calculate the z-score for a 90% confidence interval, I can just keep that in my pocket and I don't have to redo this work each time. So if I calculate that, I get 0.05. And now I'm ready to go to a calculator and calculate this. So if I'm using a graphing calculator, inverse norm is what I'm going to be using, and then it's going to want that area I just found. And then the mean and standard deviation, which this is a standard normal curve. Mean is always 0, standard deviation is always 1. In Excel, it's norm.inverse, and then the 0.05 area, mean, and standard deviation again. There is a variation on that though. I can use norm.s.inverse, and that means I'm using the standard normal curve, and it already knows the mean and standard deviation. So all I have to do is give it the area. So that is just a little quicker way to do it. So let's go to our calculator and see how that works. So in the calculator, I go second distribution. I need the inverse because I'm plugging in an area to come up with a z-score. So 0.05, and then the mean and standard deviation are already there. Now in this particular calculator, I could have just used the area of 0.9 and chose a center tail, and that would have got me the answer, but not every calculator has that option here. So I'm going to keep it with left because we did find the left tail area, and then paste that, and we get about negative 1.645. If I do this in Excel, so here's everything plugged in Excel, equals norm.inverse, grab the area, then 0 for the mean and 1 for the standard deviation, and I get the same value. If I wanted to use the norm.s, there it is, norm.s.inverse, and see now all it wants is the area or probability, and we get the same area, or same z-score I should say. Okay, so now we have our z-score. We can move on to calculating that error. So here I'm pulling over all that information that we got. I've got my error formula in front of me. I have everything I need except for Q hat. So remember, Q hat is the complement of P hat. So that's just 1 minus the 0.575 to give me the 0.425. Now I have everything I need. I'm just going to plug it in to the error formula and carefully type that into my calculator, making sure that everything in the parentheses is in the parentheses in my calculator. And I get an error 0.074. So I'm on the home stretch here. The lower limit is going to be P hat minus that error. So I get about 0.501. The upper limit is adding those two numbers together, so 0.649. And usually I will take this and put it into interval notation and turn it into a percent at that point. So multiply each of those limits by 100%. So my interval is between 50.1% and 64.9%. Now, last thing, I always want to interpret this because I want to know what the heck it means, all that work that I did. So make sure that you have the confidence level in there, what parameter you're looking at. So here it's proportion, and then of course the interval values, the upper and lower limits. So if I put all this together, we estimate with 90% confidence that the true population proportion of females at the college is between 50.1% and 64.9%. And there you have it. Now, something else that I can do before we go, that you can do with a population proportion, is find the minimum sample size you need for a particular accuracy that you want. So if I choose a large enough sample, I can increase the precision of my confidence interval without having to decrease my level of confidence. So if I take that error formula we've been using, solve it for n, I get this new formula that I can plug in all my values to and find out, well, what's the minimum sample size that I need to get the confidence interval that I'm looking for. If you don't have a sample proportion to plug in here, we're always going to use 0.5, because then when I multiply those, I get the maximum possible value for two decimal numbers between 0 and 1. So we're going to use the same information from that last problem. So I've got a sample proportion still of 5.75. And they want us to find the minimum sample size needed if we wish to be accurate within 3% of the population proportion. So that's my error. I want to be within 3%. And we're at 90% confidence level. So there's my P hat. Q hat's going to be 1 minus that. My z-score is going to be the same as before because I'm still doing a 90% confidence level. My error is 0.03 from the 3%. So I get this formula, plug all of that information in, and then calculate it. And so I get about 734.76. Now we're looking for the minimum sample size, and so we're always going to go on the safe side and round up. So even if this had been 734.1, I still would have rounded up to 735. And then one last note, if I hadn't had that P hat given to me, then I would use 0.5 for P hat and Q hat and plug everything else in exactly the same. And you can see I get a slightly higher value in this case. So having a sample proportion to estimate things does help to make our sample size smaller, which is always a plus because that's fewer people that we have to ask. But if you don't have that, we go with the highest possible option. And that is how you come up with the minimum sample size.